Hello, and today we're going to be talking about rational expressions. Now, this is a real watershed topic that'll introduce a whole huge area of algebra that'll go up from Algebra 2 to beyond. So first and foremost, what are rational expressions? Well, put simply, rational expressions are just two polynomials divided by each other. So what does that mean? Well, a polynomial, we write that like this, of course, means many terms. So it's an expression that consists of a sum of terms, a collection of terms with integer powers of x, right? So something like x squared minus 4x plus 2, that would be a polynomial. Or something like x cubed plus 2, that's also a polynomial. A rational expression, then, it's just the division of two polynomials. So we could have a rational expression of 3x squared minus 2 over x to the 5. Or we could have a rational expression of x plus 5 over x squared minus 4x plus 4. Or, we want to go even more complicated, we could have something like x times x plus 1 times 2x minus 3 over x minus 6. Anything that, when simplified, will produce a polynomial in both terms. And that includes even things like 1 to the over x, because 1 is just x to the 0 over x to the 1. So that's what a rational expression is. And as you can see, they come in varying degrees and varying forms. But why exactly are they important? Well, rational expressions have a very unique property that isn't shared by almost any other type of expression. We can see it when we start to plug in values. We start to evaluate a given expression for certain values, right? So let's say I'm given 2x plus 3 over x minus 2, right? And I want to find the value of this expression where x equals 1, right? So I plug in 1 for x, and I get 2 plus 3 over 1 minus 2. And that's 5 over negative 1, which is just negative 5. All right, simple enough. I'm just plugging in. Nothing seems to be out of the ordinary or special here. But what if I plug in x equals 2? Right? Well, in the numerator, I get 2 times 2 plus 3. In the denominator, I get 2 minus 2. So in the numerator, I have 4 plus 3, or 7. But in the denominator, I have 2 minus 2, or 0. And we know that anything divided by 0 is undefined. We can get it at a calculator, we can search it up. Anything divided by 0 is undefined. That means that for this value, for x equals 2, this expression is undefined. This is not a possible input for this expression. It may have to call this an extraneous solution. We cannot put it in and get a value out. Now this is the core of what makes rational expressions so very interesting. We will always have some value of x, right? X equals something, where if we put it into the denominator, we will get 0. Right? In this case, that x value was 2. If you put 2 into the denominator, we'll get 0. Why is that important? Because that's the value for which this is undefined for the entire expression. Right? This is very important. Oftentimes, we'll be dealing with graphing these functions or solving these functions and equations, and we need to know that there's a certain value for which this denominator is 0. And oftentimes, you'll have to find that value, because that value will not be a solution. It will not be part of its domain. It will not be defined for this expression. And part of that, of course, comes down to simplifying rational expressions. And which is, we can see why it's important, because sometimes rational expressions can be awfully huge. For example, let's say I am tasked with simplifying, let's say, x squared plus 3x over x squared plus 5x. I've given this rational expression and I'm told to simplify. Well, I kind of do want to simplify because this is kind of an awful mess. There's a lot of x's here, and I notice, hey, I have an x term on both sides. So I can actually bring this x term out on both sides, get x plus 3 times x here, and x times x plus 5 here. And I notice, well, I have an x in the numerator and an x in the denominator. So I can really just cancel out an x on both sides and I'm left with x plus 3 over x plus 5. That's nice and clean, and that looks absolutely lovely. So, we're done. Not really. This is where things get a little interesting, and another reason why rational expressions are their own huge topic. We would think, okay, well, we've simplified, so this is our complete and entire answer, nothing different, all good. And in this answer, if we plugged in x equals 0, we get 3 over 5. So we'd say, oh, it looks like just from this equation, which we simplified completely correctly, x is a valid solution. Not so. If we go back into the original expression, which by all accounts should be identical in terms of values produced to this simplified expression, because remember, simplifying doesn't change the value of the expression, we should get the same answer, right? We should get 3/5. Not true. I plug in 0 here, I get 0 squared plus 3 times 0, which is just 0, over 0 squared plus 5 times 0, which is just 0. So I get, for this, plugging in x equals 0 into this original expression, I get 0 over 0, which is plainly not 3/5. So even though we simplified this expression perfectly normally, we get expressions where if we plug in 0, we get 2 different results. Now, let's talk about why that is. Right? Remember back to what we learned previously, where if we have a given value in the denominator, it will not be a solution. It will be extraneous because it will cause that denominator to have a value of 0. Right? We notice in this denominator, we have x times x plus 5. So if x is 0, we get 0 times something, which is just 0. So our denominator will become 0 for this. Even though we cancel 0 out of both sides, we still don't have 0 existing. 0 can't exist for this original expression. This property, where our simplified expression doesn't include any points where x is extraneous, not a solution, but our original expression does, this is called a hole, right? If we were graphing this, right, and let's say, oh, it looks something like this, and we know we don't exist at 0, we'd have a hole right here at 0, where 0 just doesn't exist. And the reason is, even though we cancel it out on both sides, that hole, that place where 0 just isn't a solution, still exists here as well. So, it's a thing to keep in mind. Always look at your original expression, and even when you're canceling out stuff from the numerator and denominator, remember, that stuff in the denominator, that's still a point where it is not a solution. And of course, we wanted to practice some more and say, we could say, okay, well this, if x equals -5, this is also 0, so you could say 0 and -5 are not solutions to this rational expression. Because if we plug them in, we're going to get it so that the denominator is 0, and we know if we divide by 0, we're undefined. So we can't have that. So, to summarize, these two expressions are equivalent, right? If we plug in almost every single value, we will get the exact same answer, except 0, right? So, we have to remember and look at our solutions. And when we're factoring and we're canceling some of that stuff out from both sides, have to remember that's a hole. So that value for which the denominator becomes 0 for that value, in this case, I can just let x be 0 and it'll be 0 here, is not a solution. We got to keep track of that. Right? Now, we can try this again with something a little easier. Let's do something like x squared minus 16 over x squared minus 4, actually no, x squared minus 8x plus 16, right? So x squared minus 16, that looks like the difference of squares. I know 16 is 4 squared, so I'm going to go with x plus 4 times x minus 4. I go into my denominator here. I have, looks an awful lot like a square. Actually, that looks an awful lot like x minus 4 squared, right? So I say, oh, okay, x minus 4 squared. That's so. I simplify. I have an x minus 4 here and an x minus 4 here. In this case, it's squared, so I can just cancel this out, and I'll decrease this term by 1 because I've canceled this out. So I'm left with x plus 4 over x minus 4. Now I notice in here, hey, x minus 4 is a whole. So where x minus 4 equals 0, or where x equals 4, it isn't a solution. It's extraneous to this expression. Now this isn't particularly concerning in this case because x minus 4 is also on the denominator. So even if we cancel it out and completely forgot about it, it's 4 still wouldn't be a solution. So we're good here, but still an important thing to keep in mind. Let's go with something a little less stressful and complicated. So it's something like 6x plus 20 over 2x plus 10. Well, I can factor out a 2 here, right? Because these all seem to be divisible by 2. So I'll do that. That's 2 times 3x plus, I can divide by 2, plus 10. And of course, I can check my work by saying 2 times 3, that's 6. 2 times 10, that's 20. Pull out a 2 from here. We can just pop that 2 out of that x. And 2 divided by 10 is 5, so I'm going to have that plus 5. 2 over 2. I can cancel that out. I don't have to worry about that being a whole because that's not an x, right? I can't plug in a value to get this to be 0. It's always going to be 2. It just is. So I don't have to worry about that. So I'm left with 3x plus 10 over x plus 5. And the reason why I'm emphasizing simplifying is because it's very, very nice to take a giant, massive function and simplify it. It makes it a lot easier to work with. And I'll give an example. All right, say we have something like x squared minus 9 over x squared plus 5x plus 6. It's a pretty big thing, and this doesn't seem to be a square, so it's not like I'm going to have a nice, term here to cancel out. It seems pretty nasty and ugly to work with. My first move would always be to simplify these types of functions, of expressions. So, x squared minus 9, I'm thinking difference of squares, because I know 9 is a square. So that's x minus 3 times x plus 3. This, however, is a little tricky. No obvious tricks that I can use, so I'm going to go the standard method of factoring, which is I say, okay, I need two numbers that multiply together to get 6, but add together to get 5. I'm thinking 3 and 2, so I'm actually going to do x plus 2 times x plus 3, and sure enough, if I add them together, I get 5. If I multiply them together, I get 6, so I know they work. I have two x plus 3s in the numerator and the denominator, so I can just cancel those out. I'm left with x minus 3 over x plus 2. Now, if I wanted to say, oh, where do I have no solutions? For what values? Well, I can say, obviously, if I plug in negative 2, I'll have 0 in my denominator, so x can't equal negative 2. But I also cancel this out, which means it's a whole. So I say, well, when does this equal 0? That's when x equals negative 3. So x also can't equal negative 3, because this original expression will become undefined then, right? So the points I have to exclude are negative 2 and negative 3. And I found that first by looking and saying, I set the denominator equal to 0 and just solve for x. And I also set my any holes that I had equal to 0 and solve for x. Those are how I find my points where this expression isn't defined. Right? And that's an introduction to rational expressions. What they are, how they work, how to simplify them, and little tricks and interesting properties they have. Thanks for watching, and I hope you found it helpful. And have a great day.